Hello. So now we'll study the velocity of efflux. The thing is, we have this container, and in this container there is a water. It can be some other liquid also, and this water is till height h, capital H. So if we are having a hole in this container at a depth small h from the topmost point, some fluid will be going out. And obviously this fluid, when this fluid will be going out, its velocity will be perpendicular to the cross-section area of the hole. So that cross-section is vertical, so this fluid will be going out horizontally outward. So when this fluid will be going out, it will be following a projectile motion and it will be landing somewhere, and this distance will be capital R. So the first thing here we want to calculate is the velocity, this velocity VE. We call it velocity of efflux. We want to calculate this as a function of small h. So we'll be moving this hole and we will be calculating how this VE depends upon this height. And then we will calculate the range. So this range will also, obviously this range will depend upon this VE along with this height. So as we will move this hole, the range will also vary. So we want to calculate the VE as well as R as a function of height or depth from the topmost point. So the thing is, this portion is open to atmosphere. So here, let's assume the pressure here is P0, and that is atmospheric pressure here. And the pressure, this hole is out, obviously outside of this hole is also the atmosphere. So pressure here also will be P0. So when this liquid is coming out with velocity VE, so obviously the topmost layer of the water will be going down with some velocity. This velocity might be small, but let's take that velocity as V dash. So this topmost layer of the liquid is coming down with velocity V dash because some liquid is going out with velocity VE. So we want to calculate VE. Okay, this cross-section area, I'm defining this cross-section area as capital A. This is capital A. Okay, so for this test volume, this is my outlet and this is my inlet, which is going down. So obviously, if we apply the continuity theorem, so according to continuity theorem, whatever fluid is going down, the same fluid will be going out from this. So from continuity theorem, capital A multiplied with V dash will be equals to small a multiplied with V. Small a is the cross-section area here. Small a. This will be our equation 1. This VE as well as V dash, these two things are unknown here. So this is my one equation, and in this equation there are two unknowns. So we need one more equation. To get second equation, we need Bernoulli's theorem. We'll apply the Bernoulli's theorem. So from Bernoulli's theorem. So if we apply the Bernoulli theorem between these 2 points 1 and 2, so there is a change in depth, so we'll be using the gravitational potential energy also. So if we apply the Bernoulli's theorem, it will give us half rho V dash square plus P naught, because that's the pressure here at this point. So pressure at one point is P naught, velocity at one point is V dash, plus rho G capital H. I'm assuming gravitational potential energy at the bottom to be 0. And that will be equals to half rho VE square, VE is the velocity at point 2, plus P naught. You see, this 2 point is also outside. This liquid, when it is coming out, it is also coming out outside. So the pressure there is also P naught, plus rho G capital H minus small h. Capital H minus small h is this side. So let's rearrange this equation. If I rearrange this equation, this P naught and this P naught will cancel out. So we will get half rho VE square is equals to, we'll take this on this side, half rho V dash square plus rho G small h. Let's rearrange it further, meaning we'll multiply it by 2 and we will divide it by rho. So we will get VE square is equals to V dash square plus 2GH. This is our second equation. So if you see the second equation, there is an interesting aspect regarding this. So in this case, this layer is moving down with velocity V dash, and at this point the velocity is VE. So hypothetically, if I drop a particle from this point with velocity V dash, this height is small h. So if I drop a particle with velocity v dash from this height, the velocity at that point, we can calculate this velocity from the third kinematical equation, which says v2 square is equals to v1 square plus 2gh. So if you apply that principle, the velocity here will be v dash square plus 2gh, and that's the same velocity. So you see, if I drop a particle, it will be having the same velocity, but that velocity will be down. Since this is a liquid, the only thing which is changing here is the direction of VE. Okay, that is an interesting aspect regarding this. So now let's come back to this. So we are having two equations and two unknowns are there, V dash and VE. So let's say from the first equation, let's put the value of V dash into equation 2. If we put that value, this equation, meaning from equation 1, so it will be equals to VE square is equals to small a square into VE square upon capital A square plus 2gh. Let's bring the VE on one side. If we do that, it will be VE square 1 minus small a square divided by capital A square, and that is equals to 2gh. So this VE will be equals to, we'll take the under root, 2g small h upon 1 minus small a square upon capital A square. That will be the velocity of efflux. And as you can see, this velocity of efflux depends upon the small h. More the value of small h, the more will be the velocity of efflux here. Okay, so we get VE. So let's put this value of VE in equation 1. So from equation 1, if we put this value of VE in equation 1, we will get V dash is equals to small a upon capital A, because this will go there, multiplied with V, which is this one. So it will be 2gh upon 1 minus small a square upon capital A square. So this will become the value of V dash, and this is the value of VE. One more time. So this was a scenario when we were having a tank, and in that tank we made a hole. So the moment we will made a hole, there will be some liquid which will start going outside, and that liquid will move perpendicular to the cross-section area. So this will hit the ground at a distance capital R. So we wanted to calculate the value of V as well as the R. So to calculate the value of V, we applied the continuity theorem, along with that the Bernoulli's theorem. We got two equations, there were two unknowns. By solving these two equations, we get the value of V as well as the value of V dash. Now, we want to put one more condition. Before calculating the value of R, we want to put one more condition here. Because see, in majority of cases, this capital A is quite large compared to small a. In majority of cases. So, if capital A is very, very, very large compared to small a, in that case, you see, we are getting this term of a square upon capital A square. So, if that's the case, capital A square, small a square divided by capital A square, I can assume it to be 0. This value will be tending towards the 0. Similarly, small a upon capital A will also become 0. If we put this condition into these two equations, my value of VE will become under root of 2gh. And along with that, my value of V dash will become 0. You see, if we apply this condition, our equation, our formula becomes very easy. There is one question, when to apply this condition, when not to apply this condition. So for that we have to memorize, whenever examiner is asking some question, and if he gives you the value of capital A, in that case you have to apply this method. Meaning you cannot see that small a upon capital A tends towards 0. You cannot put that value. But in the equation, if that value of capital A is not given, you can assume this case. You can always assume if the capital A is not given, that capital A is quite large. And in that case, you can neglect small a compared to capital A, and you can directly start with from these two equations. For majority of our purposes, we use these two equations. Okay. So now we want to calculate the range. So you see, this motion, outside motion is happening along a projectile path. So we have to apply the projectile principles here. Okay. So for that we have to remove this. So we'll be solving this range now.